And as I said, we map them so we know where to go and mine them, but we also map them so we know which ones might hit us, or which ones we might attempt to deflect, etc., etc. So these are sort of some of the areas and advantages you might see in an asteroid mining case. Like I said, not technically all energy related, so I cheated just a little bit there. It was pretty cool, and I wanted to talk a little bit about the mining process. All right, so solar-powered satellites. We're going to stop mining for a while and start talking about something else. Obviously, this is what it is. Space-based solar power is what it's called. It's very important to make this distinction. Solar-powered satellites, lots of times we think of as solar, we think of that and we think, well, solar energy is powering the satellite. Yeah, we've been doing that forever. That's pretty much the way our satellite programs work. They have big solar, picture of satellite with big collectors on them. Some of them have different types of fuel cells. But a lot of our satellites use the sun's energy to to power themselves, right? So what we're talking about is space-based solar power, which is the process of using energy from the sun and basically beaming or transporting that energy back to Earth for use in electricity and other sorts of power. Right? It was first conceived of in 1968 by a guy named Peter Glasser, who was experimenting with the use of using microwaves to transfer power. You can kind of see where that application came from. If we can collect power in one place and use a microwave to transmit it to someplace else, it'd be pretty effective. They were doing a lot of those experiments in Hawaii, I believe, initially. And it sort of sat dormant for a while. That the idea was kicked around. A lot of people were writing about it. And in 1999, NASA developed something called SSERT, the Space Solar Power Exploratory Research and Technology Program, to make recommendations about the feasibility and potential use of solar power in the future. And they made several recommendations, mostly positive about the idea of using solar power. First, they thought that if we use space-based solar power collectors, that we would have a higher collection rate. What's one of the problems with solar power on Earth?
The ozone.
The ozone is one of them. Interference is one of them. What else? Say what? It is not always day is one of the big problems, exactly. Which is what they were talking about with higher collection rate. So in space, obviously the satellite has more access to the sun, can collect more energy, and be far more efficient. It's kind of tough with solar power on the Earth because sun rises and sets, clouds happen, all kinds of crap like that, and therefore we don't get a constant source of energy. SSERT also said that they had longer collection periods. This also has to do with the sun rising and setting on Earth, but not in space, which means the satellites can basically be constantly collecting the energy. That they avoided interference, like I said, cloud cover, or the ozone layer, or dust, or anything else that prevents us from having a clean shot at the sun. And finally, it was a directable power source. We could harness lasers or microwaves to transfer the power which we collected in one place and functionally beamed someplace else for use, right? So from an orbiting power station that collects it to a power station, a terrestrial power station that converts that into electricity. And that made it a whole lot easier, as opposed to terrestrial-based solar power, which is basically used like a generator and diffused from there. This can be directed to any place on Earth where we needed the energy. Much, much easier for them. A couple cool pictures of solar-powered satellites. This is an example of an artist's rendering of beaming it back to Earth. There's a few components to kind of all of them. 3 active components. One of the cells here, so it can collect the sun, obviously. The second component, which you kind of get a picture, you got an idea of from this idea in this picture here, is a way to transmit that power. As I said, probably either lasers or microwaves, both the most promising technologies in that area. And finally, there has to be a place for us to beam power to, a terrestrial power station for the adaptation of those things. Also a cool picture of the solar power satellite. Can I get the idea? This is a little short video from the European Space Agency. The sky's a little dry, but the information is pretty cool and it gives you an idea of how this process went.
From the beginning of human history, we have sought sources of energy to render our daily life more comfortable. As the centuries passed, different, more sophisticated fuels provided a corresponding evolution in available energy levels. European economy requires the equivalent of 4 kilowatts of continuous power per citizen, which is equal to 40 100-watt light bulbs. And our energy need is constantly growing, calling for reliable, clean, and safe power sources. Since the dawn of humankind to the beginning of the Industrial Revolution about 150 years ago, all our energy came from renewable energy sources. Biomass burning, wind, water, etc. The development of the 19th century was primarily based on coal burning to produce heat, steam, and drive machinery. While at its beginning, 80% of our energy came from renewable power sources and 20% from coal, this dependence was completely reversed by the Industrial Revolutions. At the end of the First World War, almost 80% of our energy came from coal combustion. 20th century technology, governed by the transport industry, electricity, industrial and material processing, required denser forms of energy provided by oil and gas, and more recently, nuclear energy. If we add to this energy triangle the total energy need, we see that it has steadily grown. While in the 20th century, world population quadrupled, power consumption increased 16-fold. Long-term, sustainable power sources must be abundant, affordable, and clean. With current technology, only one option fulfills all these requirements: the sun, the most powerful and safe natural fusion reactor at our disposal. Using direct solar irradiation on Earth is subject to weather conditions, clouds, rain, storm, etc. And of course, the natural day-night cycle. This minimizes its use for power generation, depending on the location on Earth, down to a potential of only 1/3. About 50 years ago, the first satellites identified the sun as the most appropriate power source in space. Now, we go one step further. Take advantage of permanent insolation and no weather effects in space to produce abundant power for terrestrial needs. The basic idea is very simple: to capture solar ray energy with photovoltaic panels and transform it into electricity, just as on satellites. Now, magnify this process several times and transmit the power to Earth-bound receiver sites, when and where we need it. The sun's energy on tap. While technically still some decades away, these concepts are among the most promising, sustainable, and clean energy systems. Whereas all studies have shown its conceptual feasibility, many technologies involved still need to be pushed further. At the European Space Agency, we are exploring these technologies, many of which have important potential applications on Earth.
Informative, but I don't like the big face in the picture. It was like a Saturday Night Live sketch. Anyway, so give you kind of an idea how solar-powered satellites work. Some of the debate implications of this, how the arguments function. Obviously, there's as was just stated by the video, and I think you can probably figure out pretty quickly that using solar power as an alternative to fossil fuel probably implicates for the warming would be the big advantage. We reduce the reliance on fossil fuels overall. That'd be good. Lunar stations, Mars exploration, all those deep space arguments I was making about mining apply here as well. That we would be able to, the technology, again, the infrastructure for it, being able to collect the sun on a satellite and then beam that energy basically someplace else using a laser or a microwave would make it a whole lot easier to power space stations on any planet we want to be on, and make deep space exploration more feasible. Aerospace and space power. There is amazing evidence that says that given that solar-powered satellites is a fairly achievable goal, that someplace in our aerospace industry can invest quickly and get ourselves ahead in space power. Obviously, there's a whole bunch of space power impacts like militarization, hegemony, etc., etc. But the evidence talking about the importance and of solar-based satellites because of their overall feasibility and because we're basically piggybacking on technology that already exists is really, really good. All kinds of apps can have space power kind of advantages, U.S. leadership in space kind of advantages, but few of them have a better intrinsic internal link than does the solar-powered satellites. Desalinization and water wars. The process, we can power the desalinization plants this way as well. In deeper parts of the ocean, everybody know what desalinization is, remove the salt from water so it becomes drinkable, potable water. And there's lots of excellent evidence about that. Laser and microwave weapons are also spin-offs that happen as a result of this, whether you think those are good or bad. I tend to think they're probably a little bit dangerous, but thinking about laser weapons is also very cool. But there's lots of evidence that says that the same process that we use to beam power leads to spin-offs and breakthroughs in those particular areas, makes the weapons more likely. And another one that I think is very interesting to talk about, and I don't have a picture or video of, unfortunately, are Dyson spheres. Am I familiar with Dyson spheres? Yeah? What is it?
It's a giant sphere, 1 astronomical unit in radius around the sun.
Somebody's been reading. Yeah? That's pretty much it. And how are they created?
You would take the entire Earth and turn it into the sphere.
Well, that's one of the possibilities of it. Another one is that, remember I talked about asteroids and said they're full of ore, like iron and nickel? One of the proposals for this is science fiction kind of, but it's pretty cool. A lot of people talk about it. Definitely Dyson thought it was feasible in the future, was to use solar-powered satellites to reflect the Earth's, the sun's energy back at the asteroids and melt them down, spin the asteroid, and create an environment. Anybody ever played Halo? The big Halo rings that are on? Sort of the same idea. So, pretty cool. Hopefully no aliens there to fight, but if so, I've played a lot of Halo. I'm ready. So some of the implications of solar-powered satellites for debate purposes. I want to talk about one more, and we're getting a little bit over time, so I'm going to try and get through it pretty quickly. This is not an energy source that we harness from space, but rather one that is we take into space with us, which is fission nuclear propulsion. Nuclear-powered satellites like the Cassini project, the Cassini-Huygens project, which was launched in Set 97 to study Saturn. It's powered by 32.7 kilograms of plutonium-238. Which means we basically sent radioactive fissionable material into space. Why would we do this? Well, because it is not always feasible, there's a picture of Cassini, this time in English. It is not always feasible to collect enough of the solar radiation to power the satellite, so we use a small fissionable reactor to do that. Great for deep space exploration, right? Because again, the sun's not always feasible. Good for lunar and Martian power supplies. In fact, there's a huge number of articles in like the last 6 to 8 weeks talking about the ideas for small, very small, fissionable reactors to land on the moon as part of a process of mining the moon or colonizing the moon and or Mars. Most of the literature is still focused primarily on the moon at this point, but obviously as we approach Mars, it would be the same sort of technology. And so that nuclear power would be pretty sweet for that. However, it is not always super cool. Nuclear power, obviously we found 3 Mile Island, meltdowns, things like that happen, so there's a lot of potential problems. I didn't include a whole lot of cards in this, because I didn't want it to just be a bunch of reading, but I am going to include something from this guy named Bruce Gagnon, and he's the head of the Center for Global Network Against Nuclear Power in Space, and also the father of a former North Texas debater, Julian Gagnon. And he has the following things to say, suggesting a sort of cautionary elements of moving to space. This particular card says NASA's expanded focus on nuclear power in space is not only dangerous but politically unwise, says Dr. Kaku, professor of physics at New York University. The only thing that can kill the U.S. space program is a nuclear disaster, a Chernobyl in the sky, right? So the idea being that if our fissionable reactors were to fail as part of our nuclear program, not only would they pollute the Earth's atmosphere potentially, or otherwise disrupt celestial bodies in space as a nuclear explosion might happen, but that those sort of disasters might set back the entirety of the space program. Now, to be sure, we've been using nuclear propulsion. So Cassini was the first, there's been a few others, but it's still fairly rare that we use it, and there's a lot of people who wish for us to expand it. That would be, I think, generally what the app would do. And one other card from Mr. Gagnon here. Critics of NASA have long stated that NASA's Space Nukes initiative represents the Bush administration's covert move to develop power systems for space-based weapons. The military has often stated that their planned lasers in space will require enormous power, projection capability, and nuclear reactors.